Hi ladies and gentlemen, in this video we see some important probability density functions like the uniform distribution and the Gaussian distribution. Although many other distributions are there, these two come a lot in our in this paper, digital communication. Then we will see the one important theorem that is central to statistics and probability theory, that is central limit theorem. So let me start with that presentation. First are your learning outcomes, then what's a uniform distribution, then we will see a Gaussian distribution. Gaussian distributed variables are very important in communication theory. Why, we will see by understanding the statement of central limit theorem, then with the summary of understanding. So you will learn about uniform and Gaussian probability density and distribution functions, and then you will learn to create random arrays of uniform and Gaussian PDF with the help of Python. Then you will appreciate the central limit theorem or CLT and understand the importance of Gaussian distribution in communication. Often in communication system you come across a Gaussian noise, and by central limit theorem we can argue that the noise in communication channels are Gaussian in statistics. When you think about the uniform distribution, here everything has an equal probability. The PDF is fx alpha over alpha. When we move, it is 1 by b minus a for values from a to b. For alpha from a to b, it is the value is 1 by b minus a. So it's a flat line from a to b. Everywhere a to b, it's a flat line of height 1 by b minus a from a to b. Everywhere else it is 0. So the height of it is 1 by b minus a and the width is b minus a. So the area under that curve, it's a rectangle. So the area under that curve is b minus a into 1 by b minus a, which is 1. So that's a valid PDF. And the distribution function is the integral of this one. So that looks like a straight line of shape alpha minus a by b minus a for alpha a less than b. And for alpha less than a, it is a 0. For above b, this is a 1, because we know that fx is a non-decreasing function. Its maximum value is a 1. So these two functions are plotted like this. This is the probability density function fx alpha. So if you look at alpha from minus infinity to a, it's a 0. From a to b, its height is 1 by b minus a. That's a flat line of height 1 by b minus a. And above b, it is a 0. Okay. So the area under this curve is a 1. That validates this as a this validates this PDF function. Area under a PDF is 1. Now, if I take the integral of this function, I get the cumulative distribution function. That cumulative distribution function from minus infinity to a, it is a 0. From here to here, it has a slope of 1 by, it's a straight line with a slope 1 by b minus a. Okay, this difference in height is 1, and this difference in x-axis, it is b minus a. So the slope of this curve is 1 by b minus a, and beyond b, it's a 1. So this is the shape of the cumulative distribution function. Now you can see the some demo here. You can how I will try Python 3, and from SciPy import star, from pylab import star. Okay, so if I write x equal to some rand, say 1000, it creates uniformly distributed random variables of length 1000. These are values from 0 to 1. So if I plot the histogram of this function, like x comma a 10 or 100, say, for example, you can see that the histogram shows a uniform shape. It doesn't look very uniform. If I change the bin size, you can observe this better. Like if I change to a 10, and if I plot this, you can see that it's almost flat. Okay, I have only 1000 samples, that is why we see some small changes here. It's almost a flat one. Again, what I have plotted is not a PDF but a histogram. So if I plot this x, it will look like this. Plot x. You can see this random variable. So I have 1000 uniformly distributed random variables. Okay. So this is how I generate a uniform distributed array of random numbers. Now another distribution of great importance, that is a Gaussian distribution or normal distribution. So whenever we have a large sample size, the statistics tends to be a Gaussian one. So the Gaussian PDF, that is of the equation 1 by fx alpha, that's equal to some 1 by root 2 pi sigma square e raised to minus alpha minus mu whole square by 2 sigma square, where this alpha is my variable, mu is the mean of this thing. I will come to mean and standard deviation when we discuss the moments, okay, or expectation, statistical averages. I assume that you learned this in the prerequisite course, the probability and random variables. So this mu is the mean and sigma square is the variance and sigma is the standard deviation of the random variable. So it is fx alpha, that is 1 by root 2 pi sigma square e raised to minus alpha minus mu whole square by 2 sigma square. One thing of interest is this of the form n mu sigma square of form. If mu equal to 0, if it is a 0 mean 1 and sigma square equal to 1, it conveniently defaults to the equation fx alpha 1 by root 2 pi, fx alpha equal to 1 by root 2 pi e raised to minus alpha square by 2 sigma square, when mu equal to 0 and sigma square equal to 1. Okay, that's an n01 process. So we can generate such a random variable in Python quite easily. Only thing is I have to change that rand to random. X equal to, instead of the rand, I will have say 10,000 values. Okay, rand normal. Okay, so if I plot the histogram of say 100, and if you show this, you can see that it follows almost a Gaussian statistics. You can see that it has a Gaussian statistics. Again, bear in mind that what I have plotted is not the PDF but the histogram. But you can see that the shape is the same. We can plot this function and appreciate this function. So if in any communication simulation, if you want to create say Gaussian noise, you can use this function random. I will zoom this. You can appreciate this random signal. Okay, this is how the random noise looks like. Then the distribution looks like this. These curves are plotted for this bell-shaped curve, and this is one very important distribution in almost all works of engineering. So here, this red curve has a mean of 0 and sigma or standard deviation 0.5 or variance of 0.25. And here it is moved to slightly to the right, that is with mu equal to 0.5, this curve. This mu equal to 0.5, the mean is 0.5 and sigma is 0.5. You can see that these are different same variances. Both the red curve and this light blue curve, they have the same variances. So but this deep blue curve, there is a mu of 0.5 that is here. The mean is at 0.5, but variance is bigger. Variance is 1. So you can see the change in this curve. So this curve is of utmost importance. So this is the shape of the Gaussian distribution. This height is 1 by root 2 pi sigma square. Here sigma is same for these cases. That is why their peaks are aligned. But here you can see that the sigma is less. So sigma is more. Here sigma is more. So 1 by root 2 pi sigma square, it is depressed a little. And the area under this curve from minus infinity to infinity, that is 1, because this is a probability density function. Now, once you understand this, you have to know about a central limit theorem. Probably you have learned this thing. Here I say only the statement. The central limit theorem, popularly called as the CLT, that states that if a large number of random variables, each of a different distribution, if they are added up, then the sum tends to be have a Gaussian distribution. That is central limit theorem. Say, suppose I have some random variables x1, x2, etc. say xn. For n very large, then each x1, x2, etc. have a different distribution. One may have a student distribution, one may have a uniform distribution, one has a gamma distribution, one has a Erlang distribution, be it anything. So, but if I sum up a large number of such random variables, the resulting sum, that tends to be a Gaussian distribution. So this is very important. This has a great impact in communication systems, because when you transmit a signal to the channel, a lot of noise sources are added up with that. The more the noise sources, each noise source may have its own distribution. But if a large number of noise sources are added to my signal, then the result and received signal or resultant signal coming out of the channel will have a Gaussian distribution. This is very advantage, because if I know the statistics of the noise, I can easily remove that. So it is due to the central limit theorem that most of the noise in the communication systems are Gaussian in distribution. So often when you see a lot of analysis for Gaussian noise, everywhere they assume Gaussianity. Why they assume Gaussianity is it is due to the central limit theorem. In the communication channel, a lot of noise sources get added up. Each noise source may have its own distribution, but the resultant noise, the sum of the noise, should have a Gaussian distribution. That is the impact of the central limit theorem. I don't go into the proof or anything, but this is just to demonstrate that the noise in the communication channel is Gaussian in distribution. Now, summary of understanding. Here you understood the uniform and Gaussian distributions. You understood the PDF and CDF of the uniform distribution and the PDF of the Gaussian distribution. About the CDF we will come later on. You learn to create random arrays of uniform and Gaussian PDF arrays of numbers. This will be very useful when you simulate communication channel models. You will you know how to create random Gaussian noise. Then you appreciated the central limit theorem, and you understood the importance of Gaussian distribution in communication. And that is the end of this presentation. I thank you all.